In the last lecture, we discussed on split phase induction motor in order to make single phase induction motor self-starting. In this lecture, we will discuss on the other methods by which we can make single phase induction motor self-starting. Let's continue. As it was told in the previous lecture, that capacitor type winding has three types. One is capacitor start induction run, permanent split capacitor, capacitor start capacitor run. First, let's discuss with capacitor start induction run type motor. Let me draw the circuit diagram first. Like previous one, this is the main winding. In the auxiliary winding, there will be a centrifugal switch like the previous one. And by now you know what is the function of this centrifugal switch. Unlike previous one, we are going to connect a capacitor here, an inductor, and the auxiliary resistance RA. This is JXA. This is JXC. This is main winding RM and JXM. Here we have supply voltage VAC. This is the main current, main winding current IM. This is the auxiliary winding current IA. This is the total current I. As we are using capacitor here, it is possible to make IA current leading to the VAC supply voltage. So if we draw the vector diagram, the V will be in this direction. IM current will be lagging definitely because this is inductive load, inductive and resistive load connected in series. So this is IM, and IA will have leading value. This is auxiliary current. Now, by proper selection of capacitor size, the magnetomotive force of the starting current in the auxiliary winding can be adjusted to be equal to the magnetomotive force of the current in the main winding. That means they can be made equal, main winding current and auxiliary winding current. And by selecting the correct size of this capacitor value, resistance value, and the auxiliary winding value, the current in the auxiliary winding can be made to lead the current in the main winding by 90 degree. Since these two currents are separated by 90 degree, a 90 degree phase difference in current will yield a single uniform rotating statoromagnetic field, as we saw in our previous lectures. Whenever we have two currents which are 90 degree apart from each other, and they are placed 90 degree mechanically apart direction, I think you remember, this was the auxiliary winding and this was the main winding we made. Here we had main winding and auxiliary winding. They are 90 degree mechanically apart, and we have current through this, which is main winding current IM. We have current through this, which is auxiliary winding current IA. They are electrically 90 degree apart. How is it made? By using the proper size of capacitor, inductor, and resistance value. So it will produce a rotating magnetic field which will have a uniform value and will be rotating in any of the directions. In this case, the starting torque of the motor can be made more than 300% of its rated value. If we draw the torque speed characteristics curve, this is the torque speed characteristics curve. In x-axis we have rotor speed nr, in y-axis we have tau r. This is the torque speed characteristics curve when there is no auxiliary winding and we have zero starting torque. And this is the torque speed characteristics curve when the motor is having auxiliary winding which is having capacitor start condition. So this is with capacitor, and this is the main winding only. This is 100% of the full load. This is 200%. This is almost 300% of the full load condition. So this is 100%. This is 200%. So we are getting 300% of starting torque than its rated value. So when we switch on the motor, initially the centrifugal switch is connected, so it will have this amount of starting torque. So after attaining certain amount of speed, the centrifugal switch will be disconnected and it will come back to its main winding condition, and it will move here and it will keep operating based on the load connected with the motor. Suppose this is the connected load, so the operating point will be this and the corresponding speed will be this. Remember, capacitor start motor are more expensive than split phase motors. In split phase motor, we cannot have this amount of higher starting torque. Split phase motors are used where we need moderate starting torque, but capacitor start induction run type motors are used in applications where a high starting torque is absolutely required. Typical applications for such motors are, let me write the applications: compressors, then another application is the air conditioners, in some cases highly loaded pump, etc. Here this point is ns, that is synchronous speed. We have described capacitor start induction run motor. Next we will start discussion on permanent split capacitor. So let's write permanent split capacitor type motor. This permanent split capacitor, sometimes it is called capacitor start run type motor. That means it will start with capacitor and it will keep running with the capacitor connected. Let me draw the circuit diagram, then things will be more clear to you. As we saw in the previous page, that capacitor start induction run motor has the capacitor starting circuit, which does a good job for improving the torque speed characteristics curve. So sometimes a permanent capacitor is left permanently in permanent split capacitor type motor. If we draw the circuit diagram, this is the main winding. This is the auxiliary winding where we have capacitor connected, then auxiliary winding resistance and the auxiliary inductance. This is RA, this is JXC, this is JXA, main winding resistance and main winding reactance. This is the current through main winding, this is the current through auxiliary winding, this is the total current. We have supply voltage here, that is VAC. Here we can see, unlike the other cases, we do not have centrifugal switch here. Now we know if the capacitor's value is chosen correctly, such a motor will have a perfectly uniform rotating magnetic field at a specific load, and it will behave just like a three-phase induction motor at that point. And this type of design is called permanent split capacitor or capacitor start and run motor, as we have connected the capacitor permanently without giving any option for centrifugal switch. The configuration of permanent split capacitor motors are simpler than capacitor start motors, since the starting switch is not needed. At normal loads, they are more efficient and have a higher power factor and a smoother torque than ordinary single-phase induction motors. But the permanent split capacitor motors have a lower starting torque than capacitor start motors, since the capacitor must be sized to balance the currents in the main winding and auxiliary windings at normal load condition. Since the starting current is much greater than the normal load current, a capacitor that balances the phases under normal load leaves them very unbalanced under starting condition. So if we draw the torque speed characteristics curve for capacitor-start-run motor, that will look like this. We have NR here, tau R here, and it will follow this type of torque speed characteristics curve. This is synchronous speed. We can see it's having very low starting torque, actually lower starting torque than the capacitor-start induction run motor, but the torque speed characteristics curve looks like the one which we got for three-phase induction motor case, but it will have a smoother running condition. This motor will have a constant torque. The motor is vibrant free and run smoothly without making high amount of sounds. That's why this type of motors are used in the ceiling fans, hospitals, studios and other places where silence is very important. Next we'll discuss on capacitor start capacitor run motor. So we'll have discussion on capacitor start capacitor run. As we saw from our previous discussion that in capacitor start induction run motor, the capacitor is sized in a way so that the motor can produce very high amount of starting torque. However, that amount of capacitor does not provide us smooth running under normal loading condition. That's why in permanent split capacitor type motor, the capacitor size is chosen in a way so that it gives very smooth running condition under normal load condition. But in that case, we do not get very high amount of starting torque. It happens because the starting current is much greater than the normal load current we know from our previous concepts. So a capacitor that balances the phases under normal loads leaves them very unbalanced under starting condition. And the capacitor that gives very high starting torque does not provide the uniform rotating magnetic field under normal load condition. So in order to get the both largest possible starting torque and the best running conditions, two capacitors can be used with the auxiliary windings. Let me show you how the capacitors are connected. This is the main winding as usual. We have RM, JXM, JXA, RA, auxiliary winding resistance. Then here we'll connect two capacitor. One is called C-run. That means this capacitor will be operated under running condition, and another capacitor is connected through a centrifugal switch that is for starting purpose only. That's why it's called C starting. Now when we switch on the motor, this centrifugal switch is connected and both the capacitors are under operation. So the capacitor's values are set in a way so that at starting it gets very high amount of starting torque. Now under running condition, the centrifugal switch will be disconnected, this capacitor will be disconnected. In that condition, the C-run that is selected in a way which will produce two uniform current through IA and IM. Under running condition, this is the total I, this is supply voltage VAC. And under running condition, the motor will have very smooth operation. So both the requirements are met. In this type of motor, we are getting very high amount of starting current as well as smooth running operation. Let us plot the torque speed characteristics curve here. This is NR, this is tau R. Under running condition, This will be the torque speed characteristics curve. That means when C run is connected only. C run. But at starting, when both the capacitors were under operation, the torque speed characteristics curve will look like this. This is for starting and running capacitor. So the operating line will be, it will start with higher amount of torque. Then under a certain speed condition, the switch will be disconnected and it will start following this line. And this will be the operating point if the load connected with this is having this amount of value. So this will be the operating point, and corresponding speed can be found out from this operating point. So here we are having two value capacitor motors. The larger value of the capacitor, when the capacitors are connected in parallel, the equivalent capacitance is increased. So the larger capacitor is present in circuit only during starting, when it ensures that the current in main and auxiliary windings are roughly balanced, which provides very high starting torque. And under running condition, when the motor gets up to a certain speed, the centrifugal switch is disconnected and the permanent capacitor is left by itself in the auxiliary winding circuit. The permanent capacitor is just large enough to balance the current at normal motor loads. So the motor again operates efficiently with a high torque and power factor. Generally, the permanent capacitor in such a motor is typically about 10 to 20% of the size of the starting capacitor. Finally, we will discuss on shaded pole motors. A shaded pole induction motor is an induction motor with only a main winding. There is no auxiliary winding. Instead of having an auxiliary winding, it has salient poles, and one portion of each pole is surrounded by a short-circuited coil that is named as a shading coil. Let me draw the figure, then things will be more clear to you. The configuration of shaded pole motor is very simple. There is a winding here. This is phase connection and this is the neutral connection. A short-circuited coil is placed here. This is short-circuited coil, and another short-circuited coil is placed here. These poles are called shaded poles. A squirrel cage type rotor is placed in between. Now, when a supply is provided here, the rotor starts moving in a direction from non-shaded pole to shaded pole. That means for this configuration, this motor will be rotating in clockwise direction. Now, why it happens and how it operates. Let's see the operational principle. In order to know the operational principle, we need to see the magnetic flux strength at different position due to different values of the AC current. We'll consider different sections of the AC current. Suppose the current that is flowing through this, that's having sinusoidal in nature. If we consider this portion, suppose this is the shaded portion, this is the shading coil. Let's name it shading coil. This is the current flowing through this I, and this is the time t. Suppose this current is having different region, O to A to B, again B to C. Now, if we consider this current, we know the maximum changes occur when current moves from 0 to A or O to A. When current moves from O to A, then from A to B, there is a change, but this change is not that much significant. That's why whenever we take the differentiation of the sinusoidal wave, we get the cosine wave, and the value of cosine wave here at 90 degree is 0. That means the minimum amount of change with respect to change in time is occurring here, that is the 0 change. So we can say from A to B we will have minimal amount of change in current, but from O to A we will have the highest change in current. Now when current starts flowing, there will be creation of magnetic flux here. Now when currents move from O to A of the alternating current cycle, the flux begins to increase. Here it will be increased. But when there is a rapid change in current in this region, due to change in current, there will be an induced EMF in the shading coil. So the resulting current in the shading coil will be in such a direction so as to oppose the change in flux. If we consider this as the secondary side, this current in the secondary side will tend to oppose the original current according to the Lenge's law. So the flux in this side, in the shaded side, due to the shading coil, when current moves from O to A, that means there is a high rate of change in the current, it will oppose that change. So the magnetic flux that will be produced here will be weakened, and less amount of magnetic flux will be experienced. So here very high amount of magnetic flux will be experienced, but here very less amount of magnetic flux will be experienced. This portion or this figure is for the current when it's moving from O to A. Now if we consider another condition, when current flows from A to B, actually current changes from A to B with respect to time, we can say we are having minimal amount of changes here. For our better understanding, if we consider that there is no change occurring from A to B, we are ignoring that minimal change. So as there is no change, this shading pole will not have any effect. Consequently, the flux distribution at every portion of this pole will be same. So this portion is for AB portion current. Now for the portion BC, the current is being reduced. It's coming from a higher value to 0 value. So what will happen to this? Let us draw it again. We have the shaded pole here. So this is for the BC region. Now when this region current occurs, that means current is coming from B to C, current is being reduced. At that moment the magnetic flux here will be reduced here instantly, but this changes is occurring rapidly, so that will oppose the exchange. Previously we had a moderately concentrated magnetic flux, so that moderately concentrated magnetic flux won't be changed or be reduced drastically, because this ring will oppose that change according to the Lenge's law. So the shaded pole will oppose the change, though current is reducing, but magnetic field or magnetic flux will not be reduced, because instantly this shaded pole will oppose that change. So there will be higher concentrated magnetic flux in the shaded pole side than the non-shaded pole side, because shading coil is opposing the decrease in current. So we'll have higher concentrated magnetic flux in the shaded pole side and lower concentrated magnetic flux in the non-shaded pole side. Now, if we analyze this positive half cycle for different region, we can see we had highly concentrated magnetic flux in the non-shaded pole and lessly concentrated magnetic flux in the shaded coil. Here the concentrations are same. Here we have highly concentrated magnetic fields in the shaded pole side and lightly concentrated magnetic flux in the non-shaded side. So we can say a flux is moving from this non-shaded pole. If I consider this is the resultant or highly concentrated flux, we can say this flux is moving from non-shaded to non-shaded to this shaded portion. That means this is the high concentration flux which started from the non-shaded side and it keeps moving and comes to the shaded side. Again, for the negative half cycle, same thing occurs. It's moving from non-shaded side to shaded side. So what's happening? I have a magnetic flux and a highly concentrated magnetic flux that starts from non-shaded portion and it moves from here to here. So this rotor will experience a rotating magnetic field which is moving from non-shaded side to shaded side. In this side as well, the field will start from here. Highly concentrated field will start from here and it will be moving here. So as if these fields are moving from non-shaded side to shaded side, non-shaded side to shaded side, and rotor will experience an influence of this moving magnetic field. Consequently, a small starting torque is developed in the rotor side. As soon as this torque starts to revolve the rotor, additional torque is produced by single-phase induction motor action. And the direction of this motor is from the non-shaded pole side to shaded pole side. So we can write the direction of a shaded pole motor, that is unshaded to shaded pole. So the direction of the rotor will be from unshaded portion to shaded pole. So this will be the direction. Remember, shaded pole produces less starting torque than any other type of induction motor starting system. They are much less efficient and have a much higher slip than the other types of single-phase induction motors. But shaded pole motors are the cheapest design available. So if we draw the torque speed characteristics curve for shaded pole motor, this is NR, this is tau R. The starting torque is very low, and this is the torque speed characteristics curve for shaded pole motor. The applications of shaded pole motors. Generally, shaded pole motors are used where we need very small starting torque. These type motors are only suitable for low power applications such as small fans, toys, hair dryers, etc. So up to this much today. We will continue in the next lecture. Thank you.